Okay, now let's get this discussion started. We welcome everyone to our second session for fundamentals of robotics and AI technologies webinar workshop. And tonight we are actually talking about robot controllers, sensors, and actuators. Okay, so this is of course a continuation of our previous session. And next week we are having or we're going to transition on uh, to the AI part of our webinar workshop, right? So, okay. Robotics are fundamentals of robotics and AI technologies. Just like in our other webinar workshop, we have four sessions for it. Last week, we talked about the introduction to robotics. I mean, to robots and robotics. Right now, we're talking about robot controllers, sensors, and actuators. Next week, we're going to talk about the key concepts of machine learning. And the week after that, our finale, we will be talking about artificial intelligence in robotics. And our sessions happen at 7 to 9 p.m. of Saturday. And of course, for the entire webinar workshop, at the end of it, we hope our participants to understand core robotics concepts, including components, types, and applications. So that's hopefully we achieved that last session. And then explain how controller sensors and actuators enable robotic operation. So that's what we want for this session. And for the next week, we want our participants to be able to apply basic machine learning concepts for data-driven system behavior. And lastly, at the last session, we hope our participants to be able to integrate AI and cloud tools in simple, connected robotic systems. Right? So that would be all for our entire webinar workshop. So this is what we want to achieve. And specifically for tonight's session, um, we focus on how robots perceive their environment, process information, and translate commands into physical movement, right? So this session covers the role of robot controllers, the types of sensors in robotics, the actuators and motion systems, and integration of control and feedback, right? And that would be for the first half of this session. And for the second half, we're going to have our activity involving Wokwi and Blynk. And additional, we're going to have, although not mentioned in our FB post, we're going to feature Google Colab as well. Okay, so Colab, we have been using Colab since the past two months, and I just thought why not introduce it also in this webinar workshop, and you'll see later why. Okay, so we are talking about robot controllers, and specifically, we have two options. We have the microcontrollers and the microprocessors. For beginners, our first choice would be microcontrollers because they are cheaper and they are more available and of course easier to start with. And they are easier. It's easy to work on them, especially if you have if it's your first time to work with programming and circuit simulation or circuit assembly, right? So some of the options that we have regarding microcontrollers are Arduino, of course. It has several variants like Uno, Mega, Nano. Other than that, we have the ESP32. We had the former version 8266, I think, but right now it's being phased out and replaced by ESP32. right? So this one is like Arduino, but it has a built-in Wi-Fi. So smaller and has a built-in Wi-Fi. Okay. Other options that we can consider are the STM32 and the Raspberry Pi Pico. Okay, Raspberry Pi Pico is not a microprocessor board or a mini computer. It's actually a microcontroller, right? And of course, tonight we're going to talk about sensors and actuators. Last time we introduced some of the common sensors that we would most likely encounter when we study robotics or when we explore some robotic projects. Um, some common sensors include um, temperature and humidity sensor or the DH22 module. We also have the gas sensor, which can be used to monitor LPG, CH4, or carbon monoxide within the atmosphere. That's usually in the form of the MQ5 module, especially for beginners and for prototyping purposes. Other common sensors are the ultrasonic sensors for obstacle avoidance, the CMOS camera, of course, to give vision to our robots, PIR sensor or the motion detection sensor, or if you want to have a built-in rain detector or flame detector, you can also add them in your robotic setup. Okay. As for the actuators, in robotics, the most common type of actuator that we use are the motors, electric motors. You have DC motors, servo motors, stepper motors, and sometimes we use a relay. Okay, especially if your robot is intended to control um, some large appliances or some large devices to be turned on or turned off, right? So this is a quick overview of our controllers. And um, as the brain of the system, let's know that a controller handles these things. Okay, number one, processing sensor data. Okay, the controller receives input from sensors and interprets environmental conditions. So the only way for the robot to perceive its environment is through sensors. And data that we have from sensors are going nowhere if we don't have a brain that will process it. Okay, so also of course the sensor data is meaningless if they are not processed by our controller. Okay, so that's the first one. Next, out of the process sensor data, the controller will perform decision making. Okay, this one is where the controller determines appropriate actions based on pre or programmed logic or AI models. Right. So decision making such as whether to turn left, turn right, stop or proceed, or choose A or choose B. So the things like that. Decision making is always present in our robots, and we don't want, although we can, but we don't want too much human intervention in our robots, and it will defeat the purpose if we do so. Okay, so we want our robots to be able to decide for itself. Or in other words, we want it to be autonomous. So regarding that, decision making, if we have programmed logic, meaning we explicitly defined the things to do and not to do by our robot, then that's considered automation. Okay? We specifically defined it in our code. We program the robot to do this, do that, then that's automation. Okay? Whatever we want the robot to do exactly, we have to provide the instructions for it through our code. All right. Unlike when we have AI models, we can achieve autonomous or um, what we call intelligence, right? So we don't want our robots to be limited with our checklist, the things that we listed in our code that the robots must do is considered automation only. Okay? It's not considered intelligence, or it's not enough to be considered intelligence. Um, that's why we have AI models, machine learning, and AI models that will level up our robots from um, making decisions using programmed logic to making decisions using AI. Right? So that's what we want to achieve. And of course, this is where um, we now think whether to stick with our microcontrollers or use some more advanced processing units like the microprocessor of our Raspberry Pi. Okay, so for as discussed last session, for basic and quick results, we use microcontrollers. But for more complex and more sophisticated, especially when involving multitasking, then we have to uh, it would be better to use Raspberry Pi or some other microprocessor boards instead, right? I hope you get it. Now, for motion control, of course, our robots are intended to move. Okay, so that is the distinctive characteristic of robotic systems. They are uh, machines that involve motion. Okay, so the robots have some action or mechanical action. Um, and to do that, they need commands from our controller. So the controller sends precise commands to actuators for movement. Okay, we're going to talk about actuators later. And the actuators will be just um, controlling the different robot mechanism components based on what the controller says. So when the controller says spin or move at this speed, then it will do so. Or if the controller says, okay, stop every second, okay, every second, take a pause, or you do it uh, once every uh, 30 seconds or so, then the actuator will do so, right? It will just follow whatever the controller says, right? So it's like a slave to our controller, right? The controller is the master. It provides or it gives the commands, okay? And usually it is based on the program logic or AI model, or depends on the receiving or on the input um from the sensors. Okay, the input that it received from the sensors, right? So that's the third one. Next one, we have the task execution. So the controller ensures tasks are completed according to instructions. So the controller also monitors all the tasks being performed, and that would be that usually involves a sensor as well. So there should be a feedback mechanism that will allow our controllers to perceive whether the robot has performed the correct action, okay? Or whether the robot has completed the commanded action um, based on our inputs. Okay, so monitoring plus, of course, when the controller sees that the robot has not yet performed the task, then it will repeat the command. It will send again the command, and then uh, but it depends on our programming actually. Okay, so that's I think okay. One more, we have the communication. So the the controller interfaces with other systems, networks, or human operators. But then again, like what I mentioned in the previous session, um, when we have multitasking or when we do things, different tasks simultaneously, our microcontrollers might get overwhelmed or confused. Okay, because there might be too many tasks to be taken, to be carried out simultaneously. So, with that, the microprocessors will be a better option. Okay. Especially Arduino doesn't have built-in Wi-Fi or built-in Ethernet. ESP32 only has Wi-Fi and Bluetooth, but has no wired um, Ethernet connection. Unlike Raspberry Pi, which has an Ethernet port and four USB ports that we can use to communicate with other systems or maybe with other networks. Okay, so in industries, we have programmable logic controllers or PLC. They are more rugged, they are more reliable, and they are able to handle large equipment, okay, large devices, large robotic systems. All right, such as in the building, for example, we have elevators and escalators. The PLCs handle them. Even the different building facilities like the or the different building systems like the heating, ventilation, and conditioning, PLCs actually control them, right? Just imagine that for large scale applications, large scale systems, PLCs are usually a better option. Okay, especially in manufacturing, in factories, they are a better option. So although Arduino and Raspberry Pi can do the task, but in terms of performance, PLCs would most likely have superior results. Okay, but of course they are more expensive, and problem is they are limited in terms of programming. So we can only program PLCs to a certain extent. Okay, unlike in microcontrollers and microprocessors, we can even incorporate AI and then more advanced and complex programming logic. Okay, so in short, we can do a lot more with microcontrollers and microprocessors or our embedded systems compared to PLCs, which are actually embedded systems but large scale. Okay, so large and more uh large and more intensive operations, we have PLCs. Simple but more flexible um, functionalities, we have embedded systems using microcontrollers or microprocessors. Okay, so other than Raspberry Pi, when compared to PLCs, can be a better option, most especially if we make use of what we call a robot operating system. Okay, microcontrollers don't have an operating system; they only have firmware. Okay, where we basically are a code that we embed in the in a microcontroller chip. So that's the firmware. Unlike Raspberry Pi, we install an OS to it, usually Linux based. And that means we can also install a robot operating system to it so that we can perform some simulations, We can prototype using mathematical tools like MATLAB and even Python for some advanced logic like those involved in controls, perception, planning, and decision making. Uh, in short, with ROS, we don't need to do all those things from scratch. Okay? A robot operating system can be a good start for our for building a real world robot. Okay? But by the way, we're not talking about robot toys here. Okay, what we are talking about are real world robots that have specific or have useful functions. Okay, like helping monitor the environment, helping perform some tasks that are not safe to human beings like going through the fire or going through some high areas or working at heights. So robots can be a substitute for um, human tasks that are more dangerous or more risky. Okay, so now of course they require some advanced level of programming. Okay, and if we do that from scratch, then we might get overwhelmed, right? So that is why robot operating system can be a good start. All right. But of course, you can in most cases, you can better understand how ROS works if you have already started studying robotics with microcontrollers. So microcontrollers for getting started, and then once you're okay, you try Raspberry Pi or some other alternatives, and eventually try out ROS. Okay, so that's the I think the typical progression for learning robotics. Okay, speaking for Raspberry Pi, we can do things like this. All right, so Raspberry Pi, although not as fast as microcontroller boards, but they can do the job. Um, Plus, they can even do some other things like um, sending and receiving data, um, performing some AI functions, and of course, as you can see here, sending or visualizing or sharing the video captured in a GUI or graphical user interface. Okay, just remember, if we have AI, if we have multitasking, if we have complicated tasks like those involving an application or a GUI, then a microprocessor board like a Raspberry Pi can be a better option. Okay, and once again, um, doing these things manually from scratch might involve a lot of work. Okay, and an ROS would be um a good what do you call that? Would be uh, something like a lifesaver. Okay, to get rid of all the hassles on coding from scratch. All right. So this is just one of the things that the Raspberry Pi can do, and we can do this actually with Arduino or ESP, but with less complexity in terms of um, application and GUI plus AI. Okay. So although some microcontroller boards like the ESP32S3 are now becoming like Raspberry Pi in terms of AI. So I think it's nice to check it out. ESP32S3. Okay. So what else? Right. So now let's talk about sensors. All right. Aside from cameras, we have a lot of sensors, as you can see. If this is a robot, it usually um, makes use of a lot of sensors embedded into it, right? So there's so many types of sensors, and it will take a while if we mention them all, right? But we can basically categorize them as either internal sensors or external sensors. This is within the context of robotics. So internal sensors are also known as proprioceptive sensors. So these are sensors that actually monitor the internal state of our robotic system. Okay, so they include sensors such as when the robot arm moves at a certain position, then the robot must be aware that it has moved to this position. So the robot must know what is its current position. Okay. Um, that's why internal sensors are also known as sensors that provide self-awareness to the robot. Okay. So the robot must be aware of their internal state. Okay. Like in their positions. So position sensors are also known as encoders. Also, when there's motion, then the robot must be aware of its motion, how it moves. Okay, it must be aware of how fast uh, it moves, its velocity, um, and its orientation. So whether it is facing um, um, towards a certain degree, towards west, towards east, towards north, and so on. Okay. Orientation in the X, Y, and Z axis. All right. And we can achieve that using we have a sensor called MEMS, micro electromechanical system. So it's a microchip with a built-in gyroscope that allows the system to um, monitor its velocity and orientation. So that's what our phones actually have also. If you have noticed, our phones when we use a GPS based app like Google Maps or the other one I forgot. Any maps, anything that with maps, the phone is able to check whether we are moving, we are facing at some direction, and so on. Okay. Um, Also, the tilt of our phone. Okay. If you know the 3D images in social media apps, we have 3D images that when we move our phone, when we change the orientation of our phone, the view of the image also changes. So that is made possible by velocity and orientation sensors such as the MEMS, right? And of course, the robot must be aware of its battery and power status. Okay. They must just like Baymax. If you still remember the um the one we mentioned last session, we have the movie Big Hero 6, wherein Baymax the robot. Uh, the problem I think one missing um um room for improvement for Baymax is its awareness of its battery status. It is able to measure its battery level, but I think the problem was it was too late before Baymax was able to to realize that it has a very low power left or low uh, very low battery status left. All right. So I think that's something that Baymax can be improved on, right? Again, these types of sensors help our robots be aware of their own state, okay? So that they can estimate they need some adjustments, or they need to make some corrections in their mechanical actions. All right. As for the external sensors, there are two mainly to mention. But if we categorize them, some of them can be considered vision and proximity sensors. So we want our robots to have a sense of sight. So we can put a camera or maybe some proximity sensors like ultrasonic sensors or maybe an infrared sensor, or maybe a motion sensor so that they can know what's going on in their environment. Okay, just like human beings, we can easily know what's going on with the help of our sense of sight, right? So much of the advancements in robotics and AI technologies actually became possible through the development of vision and proximity sensors. Okay. But in addition to that, our robots must be able to sense some danger or some changes when it comes to force and pressure. So we have some force and tactile sensors that uh, will provide somewhat a sense of touch and a sense of hearing. Uh, yes, for our robots. So we have so many different tactile sensors. We're going to show them in a while. As for the sense of smell and sense of taste, we have some environmental sensors, especially chemical sensors that can help the robots determine presence of some chemical substances, such as smoke, toxic gas, and so on. Okay? Or maybe they can determine the composition of a certain chemical, whether in the atmosphere or in the water or in a certain object. Okay? So here's an AI generated visualization of the different sensors that we might um, incorporate in our robotic system. Right? So this includes actuators as well, right? First, we have integrated sensory systems for perception and state monitoring, like what I mentioned earlier. We can have a camera, a LiDAR scanner, a stereo vision, or maybe some proximity sensors, right? Plus, of course, its internal state can be um, detected using battery and the health level sensors, or we can have some voltage current sensors, fault detection systems like in Iron Man, um, or we can have encoder feedback. Encoder is for, remember, encoders are position sensors. So at the same time, we can also have navigation and localization, especially for our mobile robots. They are better when equipped with GPS features, okay, or GNSS, Global Navigation Satellite System, I think. GPS is Global Positioning System, right? So they must be aware of their location, where specific point on Earth they are. Okay, and when they are moving, they can have different orientations or different tilt or pan. So it's best also to have an IMU or inertial measurement unit, and with the help of accelerometer for their velocity. Okay. Um, Gyroscope, magnetometer, and some other sensors like the UWB. With the help of our environmental sensors like temperature, humidity, CO2 gas, and sound or acoustic sensors, they are all helping our robots navigate. Okay, and of course, be aware of the environment they are navigating through, right? When it comes to sense of touch, it will be best to have haptic and tactile interaction, especially for grippers and sensory feedback. So, we can, while we're saying haptic sensors, um, they provide information on whatever the robot is touching. Okay, like if the robot touches a certain obstacle, it will vibrate. Okay, just like how our phone vibrates when we have inputted a wrong detail, or when we have clicked an invalid command. So haptics can be a good way to provide feedback to the user. Okay, but in the sense of the robot, haptics can help, especially in the robotic arms. Haptics can help them determine whether they need to exert more effort, more force, more pressure when grasping things. Okay, so some options that we can have are the small LRA, linear resonant, or the piezoelectric bimorph sensors. Um, when it comes to the actuating side, we have the adaptive tactile gripper motors, or the strain grippers that are being controlled based on our haptic information. Okay. What else? All right. So the rest are regarding actuators now. So speaking of actuators, most of our robotic systems are special for beginners for prototyping purposes. Most of the robots are being run um, are running on motors. Okay. And motors can be brushed DC, like what we have in our wheels, or a brushless DC. Or we can have stepper motors for, sorry, stepper and servo motors for incremental or partial rotations or specific angles. Okay? And aside from electric motors, other possible actuators that we can control using our processed sensor information and programmed logic are um, the pneumatic and the hydraulic uh, actuators. Okay, so we're going to talk about that in a while. All right, I guess that would be all regarding sensors. And now let's talk about the actuators. So the just like sensors, there are too many to mention also when it comes to different types of actuators. But okay, as you can see in the animation below, some actuators are meant to move in a linear or rectilinear or prismatic motion, right? So they are called Cartesian, or um, yep, they are called Cartesian, prismatic, or rectilinear robots. Some robots can move in a cylindrical manner, so they can rotate, and at the same time, they can also adjust the height they are moving in. Or they can be a polar type, okay? Like what you see here. So they can move at any direction on X, Y, Z, but using rotational movement. Scara robot, this is a more advanced one. So as you can see, it can move around, and then it has an extension. So SCAR stands for Selectively Compliant Arm for Robotic Assembly. They can also have a jointed arm robot. So this is I think the our most of our robotic arms are in this form. Okay, so it has several joints. Okay, and it can move. Usually it can move in X, Y, and Z axis. All right. So based on that, as you can see, these movements are either linear or straight line, or rotational or rotary. So that's why one way to classify our actuators is based on the type of joint, whether the joint is for linear movement or for rotary movement. So we can have a rotary actuator or a linear actuator. So that's the first classification. Or we can also base our classification on the type of power source. So we already mentioned our robots can be, most of our robots are electric. We are using electric motors, but we can also choose to have hydraulic and pneumatic types of actuators. So for a quick comparison here, okay, in terms of if our application requires a very high force output, then the best option for us is the hydraulic. Okay, like what you see in construction equipment like cranes, um what do you call it? Tractors and um bulldozers. They are normally using um hydraulic power to provide the necessary motion that requires a very high force output. Okay, and pneumatic ones are, I think, the least favorable option when it comes to force output. Electric is somewhere in the middle, right? When it comes to precision, the best option is, of course, the electric, right? The most precise ones. Next to that is the pneumatic, and the weakest among the three is the hydraulic. So hydraulic are best when it comes to force output, but not the best when it comes to precision. And same thing in terms of maintenance. So by the way, hydraulic actuators use liquids as the source of power. So, um, since they make use of liquids, then there could be leaks, and especially some some hydraulics use oil as the fluid. Okay, and that means it could get messy, and that's why it requires high maintenance. Okay, you have to change oil, you have to check for leaks, and so on. Okay, pneumatic is quite moderate, quite high maintenance, but not as high as hydraulic. Unlike electric motors, the electric actuators, they are more convenient in terms of maintenance. Okay? But in terms of cost, the cheapest one is the pneumatic, right? And the electric ones can be moderate or even higher, more expensive than the hydraulic ones, right? In terms of environmental impact, because of their leaks, the hydraulic has, I think it, it is the least favorable one. Okay, it has potential for spills. For pneumatic, because of by the way, unlike hydraulic, pneumatic actuators make use of air as the source of power. So, um, it compresses air and decompresses depending on the action, um, and it might cause some air pollution, right? Uh, Unlike in electric, it can be considered clean and efficient, especially if you are running on renewable energy. Okay, so that's a brief comparison between these three. All right. So in terms of joints, by the way, uh, this should have been shown first. All right. Um, Based on the video or the animation you have seen earlier, our robots are actually determined by the joints that they have. Okay, or the robot's motion are or is determined by the joints that it has. Okay, When we say a revolute joint, it has some um, rotary movement. When we say prismatic, linear only. When we say helical, it moves in a rotary motion, but at the same time in a linear. So just like a screw. So whenever it moves around, it moves down or moves up at the same time. Planar joint. We also have cylindrical, like what we had seen in the video. We have the spherical joint, which is able to move in all axes, X, Y, Z, rotary motion. And the universal joint, um, much the same with, or very similar with the spherical joint, right? So, um, remember that each joint must be considered, or when we are designing the mechanical aspect of our robot, we have to uh, see to it that we are using the right joints, right? Because each joint has a corresponding DOF, or degree of freedom. For example, a revolute, so like our motors, okay, servo motors and our DC motors, they are just moving around. Okay, they are just moving in a rotary motion. They can move either in a clockwise or counterclockwise form, okay, or manner, right? So that's just one degree of freedom. And in prismatic um joints, the movement can be either left or right, or maybe in another type, it can go front and back, or in another type, it can go up and down. Okay? You can only choose one of them. Left or right, front or back, and up or down. So that's prismatic, so only one degree of freedom. Okay. Helical, only one degree of freedom, although it rotates and at the same time it goes up and down. But the problem is it cannot choose only one of the two. So still, we consider that as one degree of freedom. So when it returns, for example, just like screws, when we rotate the screw like this, I'm not sure, clockwise, in a clockwise direction, in most cases, the screw goes down. Okay. But if it is counterclockwise, then it goes up. So clockwise and downward is one way, and then the opposite is counterclockwise and upward. So that's just um, a pair of two possible states. So still one degree of freedom. Unlike in cylindrical, wherein you can separate the two, you can have a clockwise or counterclockwise direction, plus you can also have a move up and move down direction. So it has both rotary and prismatic motion. So that's why it's two. Same thing with universal, but universal is more on to um, what do you call that, motion. So if the revolute rotates in one dimension, in just one axis, universal rotates in two different axes, while spherical does it in three different axes. Okay, so that's an introduction only on the degrees of freedom. And um, when we are designing our manipulation mobile robots, are some advanced robots like humanoid types, then we have to be aware of the different joints that they must have. Okay, and of course, it will come with physics. We have to review our physics, especially um, the mechanics part. Okay, we have to review the principles of statics, dynamics, especially under dynamics we have kinematics, or the kinematics, which is concerned on the position and velocity and motion of our robot. Kinetics, also the same, but it involves the reason or the cause of the motion. Okay, meaning the what force or what energy caused such motion. Okay, so we have to review them all. Um, Under physics, of course, we have to there are some principles like in the fluids that we must understand, especially if we are considering hydraulic and pneumatic actuators, like the Pascal's law. Okay, Pascal's law actually uh, it is demonstrated in these type of actuators. So remember, pressure is pressure is force over unit area. So for example, the red and the blue ones, okay, um, the according to Pascal's law, the pressure here and the pressure on the other side must be the same. So no, no. The I just reviewed the Pascal's law, right? Because it consumes our time here. Unfortunately, we cannot discuss everything. Um, Quick note, just review some principles in physics, especially those I mentioned, and that is to better understand how these things work, how our actuators provide the corresponding motion that we that our controller commands them to do so, right? So remember, sensors are inputs. Controllers will process the inputs and send an output in the form of commands to our actuators. And the actuators will make um, our different mechanical parts move. Okay, without the actuators movement, the mechanical parts will just be static. Okay. Now, another thing, it is very important to have knowledge on the concept of control and feedback. So, in short, our robot is a control system because we are controlling something. Okay. So, if there's something you want to happen, you must to control. You have to set some parameters. You have to manipulate those parameters to achieve the result that you want. Okay. So control system can be an open loop type or a closed loop type. And as you can see, the open loop type has no feedback. So that's the main difference. Um, okay. From the input to the controller to the control signal to the process to output, there's no going back. It only goes one direction. Unlike in the closed loop system, we have our input to the controller, which will produce the control signal that will be processed by our plant or by our actuator, and then it will provide the necessary output or the motion that we need. Um, and as we provide the output, the system will measure it, right? Remember the encoders or the velocity, the position sensors. So um, it will it must be aware of whatever is being um, sent to the output side. Okay, that's why we have a feedback element. We listen to it, we observe it. Okay, so that the system will be able to determine whether it has provided the right action. Okay? Because as long as it does not match with our desired input, the one that we set here, as long as there's a mismatch between what we measure and the one that we want, there will be some adjustments here. The system will continuously adjust. So, for example, input, we have a certain input, we have a certain target, and once the command has been carried out and we have the output, the system will check, okay, it will measure and check. Okay, does it match with our desired um, input or the one that we set? Um, if not, it will go through this process once again. Okay, and then check. If it's not yet matched, then continue as long as there's a difference between the desired output and the one that we measure, then the process continues on. So for example, to understand this, imagine the air conditioning system. So the aircon, um, okay, in the US they call it AC. All right. So the AC or the aircon, um, it works by, of course, first we input what should be the temperature to be maintained. Okay, so for example, let's have 18 degrees. We want it cold. So 18 degrees. So the controller will say, oh, okay, 18. And then it will send a control signal to the component that will perform the air conditioning, the actual air conditioning. So the system will do the mechanism to make the temperature reach 18. But at all times, the system will check. Okay. So once the output has been produced, okay, the system will check, is it 18? So it will send the measured temperature and check. For example, it has measured 21. So, okay, what I have here is 21. So is 18 equals to 21? No. Then repeat the process. So for example, we have 19. So we measured 19, but our input is 18. So is 18 equal to 19? No. So repeat the process until 18 becomes 18. Okay, the one that we measure here is 18, and the one that we input here is 18. So there's no mismatch. That's why the air conditioning system will eventually stop doing the process. Okay. Unless okay, it will stop making the lowering the temperature, but it continuously monitors, it continuously measures the environment. So whenever there's a change in the temperature in that room, whenever the 18 becomes 19 or something else, then it will send a control signal to perform the process again, right? So in the same way, that's how our robotic systems work as well. So for example, in the positioning part of our robotic arms, okay, each position, each motion that it performs, each position that it and that ends up with the system will measure it, and if it's not if it doesn't match with what the user um commands it to, or what the programmed logic tells it to, then it will perform the necessary adjustment. Okay, same thing with our robot cars. As long as the right speed or acceleration is not achieved, it will continuously perform the necessary change, okay, until the desired and the actual will be the same, right? And in more advanced control systems, we um, we don't just have two possible states, the lower, the higher, or the true or the false. We can have more states as well, low, mid, high, or in a rate scale of 1 to 5, we can actually have more categorical and categorical values like low, mid, high, or levels 1 to 5, or red and blue, green and yellow. We can have different levels of measurement, categorical measurement, instead of just true or false. Okay, or what we call Boolean. So we level up Boolean. From Boolean logic, we can actually have fuzzy logic for our control systems, including our robotic systems. Okay, so here we have an example, fuzzy logic controller. We can add that to our control system for our decision making. Okay, we are not yet talking about AI. So this is one option. If we can't have AI, then the next option that we have is fuzzy logic. For example, our robot has these things being measured constantly: the angle error, the sonar distance, the left infrared distance, and the right infrared distance. So they are constantly being checked. And based on the combination of these different inputs, the fuzzy logic controller will come up with a certain decision, whether to increase the left servo or the right servo, or both, or none of them. Okay, or whether to give a low, mid, high value to the left servo, low, mid, high value to the right servo, or something more. Okay, so we still just like Boolean logic, we still set some rules, and that will be followed by our robot. So this is not AI because we still have uh, predefined rules. Unlike in AI, the robot itself will come up with its own um, new rules based on its baseline, or the one that we provided initially. Okay, so in that case, the decision making will be more advanced in terms of AI. But for now, since we are not yet on the AI part, fuzzy logic will do. Okay, especially for beginners, right? And it's best to be partnered with what we call a PID control system. Um, it will be more complicated. It's quite mathematical heavy. Um, just remember a PID sensor. For example, what we want from a low state or an off state, okay, a low state to high state. In reality, it doesn't just switch. Okay, it has some transition actually. Okay, it's not a straight uh line. Okay, so what we want is a straight line. Okay, we don't want the curves. We don't want the variations. So to to get rid of these variations, or to minimize these variations, we can have a PID controller. So once we have our command from our logic, whether we are using Boolean logic or fuzzy logic, okay, we will send it to our PID controller, which will um, try to improve the stability and the responsiveness of our control system. Okay, and in most cases, when you download uh, an instant code from the internet regarding a robotic system, in most likely you will see a formula there in the code that includes a PID controller. Okay, especially for the more precise types of robotic systems. Okay, but for this one, I think this is quite basic. It doesn't have a PID part yet. Okay, so right, unfortunately, we cannot demo that part on the PID. This is just an additional and still part of the feedback. Okay, what we want to emphasize is the feedback part. So as long as we don't achieve our desired output, we continue to make adjustments. So that's the purpose of feedback, right? So before we talk about the activity, by the way, that's the end of our first half. Okay, our discussion. And before we proceed with the activity, let's watch this video.